This is part 2 of a series on batch normalization. In this video, we will implement a custom batch normalization layer using Keras. This video was produced in Korean and translated into English. My voice is AI-generated text-to-speech. In the previous video, we looked at how batch normalization works during training and prediction. In this video, we will implement this in code. First, let's create a simple neural network with Keras' batch normalization and see how the internal parameters of the batch normalization layer change before and after training. Then, let's implement batch normalization layer from scratch using Keras' custom layer. Finally, we will experimentally verify whether the neural network model with the batch normalization effectively prevents overfitting. Let's create a simple neural network using Keras' batch normalization and see how its parameters change before and after training. Import Keras' batch normalization class. Generate a simple dataset. Set the epsilon to 0.001 and the rho to 0.99. The epsilon is a small number that prevents the denominator from becoming 0 when normalizing h. The rho is a hyperparameter used when calculating exponential moving averages. Now let's create a neural network model like this. Create an input layer and create a hidden layer with 4 neurons. We did not use any bias in this hidden layer because the beta acts as a bias. The name of this layer is HN. Next, create a batch normalization layer. The momentum is set to the rho value, 0.99, and the epsilon is set to 0.001. This layer takes H as input and outputs R. The name of this layer is BN. Apply ReLU activation function to R. And add an output layer. Create a model for training and compile it. And we create 2 additional models to check the outputs H and R. Let's look at the summary results of this model. HN dense is this layer and the output is H. H is a none by 4 matrix. None means the batch size of input data. This is known when the data is entered. WH is a 3 by 4 matrix. Since this layer has no bias, the number of parameters is 3 times 4, or 12. The output of the BN layer is R, which is also a none by 4 matrix. The parameters of the BN layer are gamma, beta, mu EMA, and sigma squared EMA. These are all vectors with 4 elements. 4 is the number of neurons in the hidden layer. Therefore, the number of parameters in the BN layer is 4 times 4, or 16. The gamma and beta are trainable parameters that are updated via gradient descent during training. However, mu EMA and sigma squared EMA are not updated by gradient descent, but are computed using the exponential moving average formula. Therefore, they are non-trainable parameters. Of these, 4 is the size of mu EMA, and 4 is the size of sigma squared EMA. The number of parameters in the output layer is 4 for WO and 1 for BO. Let's check the internal parameter values of the batch normalization layer. Since this is before training, these values are all initial values. The getWeights function of the BN layer allows us to obtain the gamma, beta, mu, and the variance values. Now let's fit this model to the data. After training, we feed data X into this model and check the outputs H. And we feed data X into this model and check the outputs R. Next, we check the internal parameters of the BN layer, which are gamma, beta, exponential moving average, and variance. Finally, we manually compute the matrix R, which is the output of the BN layer, using this formula and compare it with the results above. Let's check the results. The initial values of gamma and beta are 1 and 0, respectively. The initial values of E of H and VR of H are 0 and 1, respectively. These are all vectors of size 4, which is the number of neurons in the hidden layer. After training, the matrices H and R are as follows. The number of rows is the number of input data points, but only 3 rows were output. The gamma, beta, exponential moving average, and variance are as follows. These are also vectors of size 4, which is the number of neurons in the hidden layer. Finally, the matrix R calculated manually using this formula is as follows. This agrees well with the results above. Let's run this code. The results are as follows. Next, let's implement a custom batch normalization layer using Keras' custom layer. We generate and save a dataset for binary classification like this. This data will also be used in the next code. Read the save training and test data. Visually see the distribution of the data. Now we implement our custom batch normalization layer class. The class name is myBatchNorm. This class inherits the layer class from Keras. The inputs to this class are the number of neurons and the row. Write a build method to generate internal parameters. Later, when the data H is input to this class, the shape of H will be passed as the input shape argument. The input shape will be M by K. M is the batch size of the data X, and K is the number of neurons in the hidden layer. We use TensorFlow's add_weight function to create variables for the internal parameters gamma, beta, exponential moving mean, and variance. All initial values of gamma are set to 1, and all initial values of beta are set to 0. And since the gamma and beta are trainable parameters, we set the trainable argument to true. Then Keras will also update the gamma and beta during backpropagation. The initial values of exponential moving average are set to 0, and the initial values of exponential moving variance are set to 1. And since these are not trainable parameters, we set the trainable argument to false. All of these parameters are vectors with k elements. Next, we write the call method. This method is automatically called when data is entered into this class. The input data matrix H is passed as the inputs argument. And if the training argument is true, the training process is performed. And if it is false, the prediction process is performed. During training, the input matrix H is normalized using this formula. This formula uses the mean and variance of H. During prediction, the input matrix H is normalized using this formula. This formula uses exponential moving average and variance instead of using the mean and variance of H. Their initial values are 0 and 1 respectively. We output this message to check if this part is actually executed during prediction. We normalize the matrix H using these formulas. And we use these formulas to update the exponential moving average and variance. These are used in the prediction process. And we get the matrix R using this formula and return it. Now let's create a neural network model like the one in the right figure with batch normalization applied. The number of neurons in the hidden layer is set to 128. The batch size is set to 300, and the row is set to 0.99. Initiate the custom batch normalization class we just created. The inputs of this class are the number of neurons in the hidden layer and the row value 0.99. Create an input layer and create a hidden layer. There is no need to use bias in this layer. This is because the beta in the batch normalization layer acts as a bias. And we add the batch norm layer we just initiated to this model and input H. We apply ReLU activation function to the outputs of this batch norm layer. Finally, we create an output layer. Create a training model and compile it. Fit this model to the data. After training, check the history of loss visually. And measure the accuracy of the test data. Finally, check the parameters stored in the batch norm layer. Let's check the results. As training progresses, the loss decreases like this. The reason why the validation loss is high initially is due to the initial values of the internal parameters of the batch normalization layer. And in the prediction step, you can see that the training argument of the call method of the batch norm class is passed as false. The accuracy of the test data is 0.81. And the internal parameter values of batch normalization are as follows. These are all vectors with 128 elements. You can see that they have been updated from the initial values to these values. Let's run this code. The results are as follows. The internal parameters of batch normalization are as follows. Finally, let's implement a neural network model with Keras Batch Normalization layer and see if it prevents overfitting. We will use this data that we saved in the previous code. Create a neural network model. Create an input layer and a hidden layer. Then we add a batch normalization layer to this model and apply an ReLU activation function. And we add 10 more hidden layers. The data is simple, but we intentionally added many hidden layers with batch normalization to this model to verify the effect of batch normalization. Create an output layer. Then create a training model and compile it. Fit this model to the training data. Observe the changes in loss during training. Let's check the results. If you don't apply the batch normalization, you can see that overfitting occurs like this. But if you apply the batch normalization, you can see that overfitting does not occur like this. For this data, the accuracy of the test data was measured to be slightly lower than the left, but this model is more stable. The left model is unstable, which may result in poor accuracy on new test data. However, since this model is stable, it is unlikely that its accuracy will decrease even if new test data is used. In this way, you can see that applying batch normalization can prevent overfitting like regularization or dropout. Let's run this code. First, let's remove the batch normalization layer. You can see that overfitting occurs like this. Next, let's apply the batch normalization. You can see that overfitting does not occur like this. So far, we have discussed batch normalization through 2 videos.